In the today's class, we will take up the applications of Bose-Einstein statistical distribution function. In that, we will try to derive the Planck's law of radiation using Bose-Einstein statistical distribution function. And at the later stage, we will also come across the Wien's displacement law or Wien's law of radiation and the Rayleigh-Jeans law. So three important laws of radiation can be understood by using this Bose-Einstein statistics. Basically, the Planck's law of radiation is applies to the photons. Okay, photons are the packets of energy corresponding to the radiation. So radiations are assumed to be having the packets of energy, and those packets of energy are having the energy E equal to h into nu, where h is the Planck's constant, nu is the frequency of radiation. Basically, Planck's law of radiation is defined in terms of energy density, that is energy per unit volume, that was defined by Planck. Later, the energy of the photon is assumed to be E equal to h nu, that is the packet of energy, and energy of the radiation is discrete. So it is not continuous, it is discrete. That is the basic thing behind this Planck's law of radiation. So let us try to derive this. Let us consider a perfectly blackened enclosure of volume V, which is filled with radiations at temperature T. Let us take a perfectly blackened enclosure, because perfectly blackened enclosure will not allow the radiation to go out, and also it will not allow the radiation to come in, so that it is an isolated enclosure. So energy cannot be exchanged with the surrounding. And volume of the enclosure is assumed to be V, and temperature of the enclosure is T. Okay. Now the radiation is considered as a collection of photons, and system may be regarded as system of photon gas. And this enclosure is consisting of radiations, and these radiations act like a photon gas. Okay, so photons are moving randomly, just like the gas molecules. These photons have unit spin. They have the spin unity, and therefore they obey Bose-Einstein statistics. You can apply Bose-Einstein statistics to these photons. Okay. Let us apply that. Let us apply this Bose-Einstein statistics to the photons. First, you will try to find out what are the number of photons having the energy between E and E plus dE, that is given by N of E into dE is equal to G of E into F of E into dE. So this is the basic equation determining the number of particles having the energy between E and E plus dE, or having the energy E. So that is always equal to the product of the density of available states into distribution function. That is very basic equation in statistical mechanics. Number of particles is always equal to density of state into distribution function. Okay. Here density of state G of E into D is the density of states of photons with energy between E and E plus D. Okay, they are the number of available states or number of energy levels. And F of E stands for statistical distribution function, which is here Bose-Einstein distribution function in the present case, because this distribution function which is applicable to the photon is Bose-Einstein distribution function. So basic equation says number of particles having the energy E is equal to density of states, number of states available with energy E, into the distribution function, which is a function of energy E again. Okay. Now this is the basic equation already you have written. Now we know that the distribution function corresponding to Bose-Einstein statistics is FBE of E is equal to 1 divided by E to the power alpha plus E by KT minus 1. That is basically Bose-Einstein distribution function. We have to substitute this distribution function here, and also we have to find the density of state. If you substitute the distribution function, you will get N of E into dE, that is equal to the density of state G of E divided by this term e to the power alpha plus E by kt plus minus 1, alpha plus E by kt minus 1, okay, into dE. So this is the number of particles having the energy E, or number of photons having the energy E. Now we know that in terms of momentum space, or in momentum space, the density of state having the momentum between P and P plus dP, that was given by G of P into dP equal to V by H cube into 4 pi P square into dP. Already you have studied in one of the previous classes. We have given the expression for density of state in momentum space, density of state in energy space also. So this is basically a density of state in momentum space. Okay. So here, number of available state having the momentum P is given by V divided by H cube into 4 pi P square into dP. Okay, this is the basic equation. I am not going to derive it. Already you have discussed in one of the previous classes. I will not spend much more time here. Now, this is the number of available state. But here, in case of photons, there are two independent directions of polarizations. Okay, longitudinal polarization and transverse polarization. Basically, they have two allowed momentum states. So in a given momentum state, you can accommodate two photons, one having one particular polarization and another with the other direction of polarization. That means two photons may occupy the same state, but they differ by their direction of polarization. Therefore, the density of state is the twice as the above density of state. So actual number of photons accommodated, that is equal to 2 times the density of state here. So you have to multiply it by 2, because you can find two photons with opposite polarization, okay, different direction of polarization in a given state. So these are the number of available state. G of P dP represents number of available states. In each state, two photons can be accommodated. Therefore, you can get the actual number of available state equal to 2 times of this one. So therefore, the actual number of available state G of P into dP equal to V by H cube into 8 pi P square into dP. So you have to multiply it by 2, that's all. So just you observe, we have substituted for distribution function here. And now we are trying to find out the density of state. Okay. Other you find out you can get number of photons having the energy. That is our aim. We have to find N of E. We need density of state. We need distribution function. Distribution function is already known to us. We have to find out the density of state for these photons. Now this is in terms of momentum space. Convert this into energy space. Okay. Now energy of the photon of frequency nu is given by E equal to hd. That is actually the energy of photon, where h is the Planck's constant, nu is the frequency of that photon. Then for photons, momentum in terms of wavelength and frequency, that is given by, you have to express the momentum P in terms of wavelength, and you have to use the de Broglie hypothesis. According to de Broglie hypothesis, this momentum P is equal to h by lambda. That is always true. If you go to the quantum mechanics, you will study that. But here, you believe me, momentum of the photon P is given by h divided by lambda. Okay, where h is the Planck's constant, lambda is the wavelength of radiation. Now you can express this lambda as nu by c. Okay, wavelength lambda is always equal to c by nu. So therefore, you can get this momentum P is equal to h nu by c. Okay. Basically, the velocity of light c is given by wavelength into frequency. Okay, velocity of light c is equal to wavelength into frequency. Therefore, 1 by wavelength, 1 by lambda is equal to nu by c, frequency divided by velocity. That is what we have substituted here. Okay. So P is equal to h by lambda, that is equal to h nu by c. So we have expressed this momentum P in terms of frequency of radiation. Okay, what is this h nu? H nu is nothing but energy. So momentum P is always equal to energy by velocity. That is always true for photons. Now you have to find out dP, because we need P here, we need P and dP here. That's why we try to express this P in terms of frequency and dP in terms of frequency. Now if you obtain P, that is equal to h nu by c, therefore dP is equal to derivative of this P will be equal to h by c into d nu, because h is constant, c is constant, nu is variable with respect to the variable momentum. So dP is equal to h by c into d nu. Now substitute this P and dP in this equation, that is g of P into dP equal to V by h cube into 8 pi P square into dP. Here you substitute for P and substitute for dP. Then the density of state with frequency between nu and nu plus d nu will become equal to g of nu into d nu is equal to V by h cube as it is. You substitute for P as h nu by c. So it will be 8 pi into h nu by c the whole square into h by c into d nu. So we have expressed this density of state in frequency space in terms of frequency. We have converted this momentum into frequency. Okay, completely you have converted that momentum into frequency. And look at the expression here. It contains the frequency nu. Momentum is eliminated here. Momentum term is eliminated. So finally, if you simplify it further, here h square and here h cube gets cancelled. Here you will get a nu square divided by c cube, c square into c cube. So g of nu into d nu will be equal to 8 pi v divided by c cube into nu square into d nu. So this is the density of state in terms of frequency. Now we have to find the number of photons having the energy E, okay, using the previous equation. If the enclosure is at constant temperature, the walls of the enclosure will absorb and re-emit the photons continuously. So emission and absorption of photon is going to take place in the walls of the container, okay, walls of the enclosure. Because of that, the number of photons are not constant. So number of photons are going to be variable. But in the derivation of distribution function, that is Bose-Einstein distribution function, we have used the conservation of number of particles. So you have taken summation of dni equal to 0. You can recall that, otherwise you can go to the previous class. We have seen that summation of dni equal to 0, and we have multiplied that equation by minus alpha, where alpha is considered to be non-zero constant. Summation of dni is taken to be 0, okay, while deriving the Bose-Einstein distribution function. To solve this difficulty, here in this case, photons are not constant, that is summation of dni is not equal to 0. Therefore, the Lagrange's multiplier minus alpha should be equal to 0. Okay, so this applies to only photons, not for all the particles. For other particles, this alpha is non-zero. Summation of dni is 0. But here for photons, summation of dni is non-zero and alpha should be equal to 0. Okay, so that will not make the identity minus alpha into summation of dni equal to 0. The validity of this equation will not be violated if alpha equal to 0. Here in derivation of Bose-Einstein statistics, we have taken this term as 0. We have taken summation of dni equal to 0. But basically, this alpha is 0 in case of photons, where the summation of dni is not equal to 0. Therefore, this alpha should be equal to 0 for photons. Therefore, the distribution function or the expression for number of photons having the frequency nu, that is n of nu into d nu, is equal to density of state into the distribution function f of e, where we have to take alpha equal to 0. So you will get 1 divided by e to the power e by kt minus 1. So basically we have e to the power alpha plus e by kt. Alpha is 0 here. Therefore, you will get e to the power e by kt minus 1 into d nu. Now substitute for this density of state. So density of state is already derived in the previous slide. Therefore, number of photons having the energy nu into d nu is equal to 8 pi v divided by c cube into h square divided by e to the power h nu by kt. Here I have substituted E equal to h nu, that is energy of photon, minus 1 into d nu. So this is basically giving you the number of photons having the frequency nu. Okay. Here energy of the photon is expressed as E equal to h nu. So finally, we have to find the energy density. So energy density is given by energy per unit volume, total energy per unit volume. So energy density of the photons of frequency ranging between nu and nu plus d nu is given by energy density epsilon nu into d nu, that is equal to total energy divided by volume into number of photons. So E represents energy of one photon. Energy of one photon into number of photons gives you total energy. So total energy divided by volume, that gives you energy density. Okay. So substitute here, substitute for E, substitute for n of nu, and simplify it further. So E is equal to h nu, V is kept as it is, and substitute for n of nu into d nu. So that is equal to 8 pi v divided by c cube into h nu square divided by e to the power h nu by kt minus 1 into d nu. Now simplify it, volume gets cancelled, V gets cancelled. Here h nu, it will become nu to the power 3, nu cube you will get. So finally, the energy density epsilon nu into d nu is equal to 8 pi h divided by c cube into nu cube divided by e to the power h nu by kt minus 1 into d nu. So it says that this energy density of the radiation is directly proportional to frequency cube. That is basically the Planck's law of radiation. Okay. So this energy density of radiation is directly proportional to the frequency cube. And also for higher frequency, the energy density is going to decrease exponentially. So this is the famous Planck's law of radiation, which states that the energy of radiation is discrete. Okay. This derivation of Planck's law was given by Bose in 1924, and it is called as Bose's statistical derivation of Planck's law. Okay. So this gives you the variation of energy density with respect to the frequency of radiation. Initially, for lower frequency, this energy density is directly proportional to the cube of the frequency, and for higher frequencies, this decreases exponentially. So that is what the Planck's law of radiation says, and it explains the black body radiation spectrum. Okay, so just I will try to show it to you how this black body radiation spectrum looks like. Okay, so just I will try to complete this Planck's law of radiation in terms of wavelength also. If you express this in terms of wavelength, how does this energy density looks like? So let us see that. Here Planck's law can be expressed in terms of wavelength of radiation also. So what you have to do, you have to express this frequency nu in terms of lambda. So substitute this nu is equal to c by lambda. That is the basic equation. C is equal to nu into lambda. Therefore, nu is equal to c by lambda. That is velocity by wavelength. If you differentiate this one with respect to nu, d nu will be equal to c into derivative of 1 by lambda. Derivative of 1 by lambda is 1 by lambda square into d lambda. Now substitute this d nu and nu in the above equation. Okay, so that will give you epsilon of lambda into d lambda is equal to 8 pi h divided by c cube. In place of nu cube, you substitute c by lambda cube into 1 divided by e to the power h nu by kt ಇದ್ದಲ್ಲಿ ಏನಾಗಬೇಕು ನೀವು you substitute for nu as c by lambda, you will get e to the power hc by lambda kt minus 1. In place of d nu, you substitute c by lambda square into d lambda. Okay, this is basically d nu. D nu is expressed in terms of lambda. And simplify it further, cancel the terms which are going to get cancelled. Here c cube gets cancelled. You left with 8 pi h into c. This c is taken here. Here lambda cube into lambda square, you will get lambda to the power 5 into 1 divided by e to the power hc by lambda kt minus 1 into d lambda. So this is basically called as Planck's law in terms of wavelength. So here also the energy density in terms of wavelength can be represented as it is inversely proportional to lambda to the power 5, and also it decreases exponentially for shorter wavelengths. Okay, so for shorter wavelengths it is inversely proportional to lambda to the power 5. For higher wavelength you will get this for longer wavelength this energy density is directly proportional to inversely proportional lambda to the power 5. For shorter wavelength it exponentially decreases. Okay, so this is basically the law, Planck's law of radiation in terms of the wavelength of radiation. Okay, so if you plot the graph of this energy density, so how it looks like, so that I will show you. So Rayleigh-Jeans law I will consider later. So just I will try to show it to you how this energy density looks like, graph of energy density looks like. So just a minute. This graph shows you the energy density versus wavelength graph. Okay, so for shorter wavelength, you can get the increase in energy density and reaches the peak value, and then it decreases exponentially if you go towards the longer wavelength side. Okay, so this is observed for different temperatures here. It is observed that the increase in temperature makes the energy density curve to shift towards the lower wavelength side. The peak value of the energy density shift towards lower wavelength side. And here it is visible region is observed here. This band shows the visible region. So the black body, otherwise a body emits radiation if its temperature is around 5000 Kelvin. Okay, the peak value of radiation energy density is observed in visible region if temperature of the body is around 5000 Kelvin. If temperature is lower, the body will emit the radiations in infrared region. If temperature is much higher, the body will radiate the energy in ultraviolet region. Okay, that is how we can understand the concept of Planck's law of radiation. It gives you the energy density as a function of frequency as well as energy density as a function of wavelength also. And it explains the experimentally observed energy density of black body using this theoretical concept. So Planck's law of radiation gives you the energy density emitted by the body, okay, as a function of wavelength. But classical theory gives you this particular curve, so that cannot be explained. That cannot explain the experimentally observed facts. But quantum mechanics, otherwise Planck's law of radiation, explains the experimentally observed curve corresponding to the black body. And also the shift in the peak of the energy density can be observed with increase in temperature, and that is called as Wien's displacement law. And we'll come to that later. In the next class, we'll consider this Wien's displacement law also.